Let's evaluate the performance of a heat pump, which we've done multiple times in the past. We always did that with an energy balance. Let's do it again, only this time let's use an entropy balance. The heat pump cycle shown below operates at steady state and provides energy by heat transfer at a rate of 15 kilowatts to maintain a dwelling at 22 degrees C, when the outside temperature is minus 22 degrees C. The manufacturer claims that the power input required for this operating condition is 3.2 kilowatts. Applying energy and entropy rate balances evaluate this claim. So here's the schematic of a heat pump. The system we're evaluating is this heat pump, which operates between this cold thermal reservoir and this hot thermal reservoir. So power is put into the heat pump. The manufacturer claims 3.2 kilowatts is required. And that causes heat to transfer from the cold reservoir into the heat pump via heat transfer, and for energy to transfer from the heat pump into the hot reservoir by heat transfer. Now we're going to model this as a closed system, and we're going to ignore any changes in kinetic and potential energy. And we're going to evaluate this claim two different ways. We're going to do it with an energy balance, which we've done with previous problems. But we also want to do it with an entropy balance. So we can write an energy balance. dEdt is zero. It's zero because this cycle operates at steady state. And all properties in a steady state process are constant with time. So dEdt is zero, and that's equal to Q dot minus W dot. Well, therefore, Q dot is equal to W dot. Or we can say, we can expand this Q dot term since there's two Q's. We know that W dot is Q dot H, which is a transferring to our hot reservoir, minus Q dot C, which is transferring energy into the heat pump. So this equation here we have derived many times in the past, and it's true for all power cycles, refrigeration cycles, and heat pump cycles. Now the coefficient of performance we've defined in the past. So for a heat pump we called it gamma, and we've always defined it as what we want divided by what it costs us to get it. Well, for a heat pump, we want to keep the warm side warm, so we're interested in this Q dot H term. What it costs us is the power input, the W dot term. So the coefficient of performance is just Q dot H over W dot. Well, the Q dot H was given as 15 kilowatts. The power input was given as 3.2 kilowatts. So the manufacturer's claim is that the coefficient of performance is 4.6875. Well, let's see if that's possible. We know that the maximum theoretical coefficient of performance is only a function of the temperatures of the hot and cold reservoir, and is not a function of any particular parameters of the heat pump. And also in the past, we've derived this expression for gamma max as just being TH over TH minus TC. Well, we always use absolute temperatures, so the TH is 295 K, TC is 251 K, and we get the maximum theoretical COP that is possible for heat pump operating between these two thermal reservoirs is 6.705. Well, the calculated coefficient of performance is less than the maximum theoretical. So that means this heat pump performance is possible. So now let's evaluate the same heat pump with an entropy balance. We know that the change of entropy around a cycle is zero, and that's because the cycle ends where it begins. So the change in any property around a cycle is zero, and entropy is a property. Well, delta S for the cycle is equal to the summation around the cycle of Q dot over T. And that's a term that represents all of the entropy that's brought into the system by heat transfer. And then we add to that the rate of entropy production that is produced within the system during the cycle. Now, since this summation plus sigma dot is equal to zero, we can say that the negative of the entropy production rate around the cycle is just the summation around the cycle of Q dot over T. Well, there are two heat transfer terms. There's Q dot C and Q dot H. So let's replace this summation with Q dot C over Tc, which is the temperature at which this heat transfer takes place. And we'll sum with that Q dot H over Th. Now, that means then that the negative of the entropy production rate around the cycle is Q dot C, and a simple energy balance will yield that Q dot C is 11.8 kilowatts. We'll divide that by the cold reservoir temperature of 251 Kelvin. Now we're going to add to that Q dot H over Th, but Q dot H is a negative 15 kilowatts. It's negative because energy is being removed by heat transfer from the system. It's not being added to the system. And that takes place at 295 Kelvin. So when we do the math, we get that the rate of entropy production around the cycle is 0.0038 kilowatts per degree Kelvin. Now this entropy production is positive, and therefore this is a possible cycle to take place.